Hello everyone, my name is Prantapatim Roy. Today I'll be representing our project titled Solving the Electric Vehicle Routing Problem, Integrating CSP, ZT Heuristic and Meta Heuristic with a React frontend, along with our group members Saurav Kumar, Aditi Thakur, and Swagata Dalai. The Electric Vehicle Routing Problem, or EVRP, is a logistic optimization challenge. We are given a fleet of vehicles that need to pick up and deliver items throughout a city. These vehicles start and end their journey at a central depot. Each vehicle has a limited battery and weight capacity. The energy consumption depends on both distance traveled and load carried by the vehicle. If the battery level drops below 15%, the vehicle must recharge itself at a charging station, which has limited number of ports, and it follows a first come first serve policy. The goal is to find the most efficient routes for all the vehicles that minimizes the energy consumption but still fulfilling all delivery and pickup tasks under these constraints. Here you can see a visual representation of EVRB. There is a depot and multiple customer nodes with their pickup and delivery demands and distances between locations. The challenge is routing multiple vehicles while satisfying weight, energy, and charging constraints efficiently. Now, why this EVRP is important? With the rise of electric vehicles in logistics, efficient routing has become critical. Electric vehicles come with challenges like limited battery range, charging station access, load dependent energy use, etc. etc. By solving EVRP, we can help logistic companies to reduce operational costs, improve delivery times, and also we encourage greener, smarter urban mobility systems. This kind of optimization is essential for building eco-friendly smart cities. Many major companies are already tackling such kind of problem in real time. Like Amazon is testing electric vehicle fleets with Rivian vans, focusing on reducing charging stops. UPS has integrated route optimization algorithm to save energy and time. DHL uses street scooter electric vehicle fleet with intelligent routing to cut delays. FedEx uses AI to optimize electric vehicle routes in real time. These are the examples so that EVRP is just not a theoretical problem, it's a real world issue. And its industries are actively working to solve this. Now, our project is divided into two parts, front end and back end. Our project's front end was developed by React, which is a popular JavaScript library. The interface displays the city map, customer nodes, charging stations, and vehicle routes. Users can set number of vehicles, can set pickup and delivery data at customer nodes, can select which algorithm to run, whether that could be CSP or heuristic or meta heuristic. How to run the project. For that purpose, open any code editor. In my case, I have developed this project using Visual VS Code, Visual Studio Code. You can open any of the code editor according to your wish. And after that, open the folder. Like in my case, I went to the open folder and here React YT. This is the file which is already open in my text editor. That's why I'm not opening it again. So just select the folder and click on select folder. You can see this screen will appear. It means that the folder that in which our project has been developed that has been opened by Visual VS Code. Now after that we have to create one terminal to run the backend at first. At the beginning we'll run the backend, so for that purpose, I will switch to our virtual environment that has already been created. For that purpose, I first write CMD to come out of the base environment. Then I will enter into the uh, folder where that backend files are stored. For that purpose, I will write React YT, and then inside React YT there is another folder named backend. You can see that backend. Enter. Yes, we are inside that. We are inside backend folder inside React. Now I will run the command. As you can see, that is written in readme.txt plus run. As you can see, the backend server is up now. Now I'll run the front end server. For that purpose, I'll create another terminal, and similar thing I'll do. I'll first come out from the base environment. For that, I'll clear type. I'll run that command cmd. Now we are out of that base environment. Now again, I will enter into that React backend into React. Now I will React YT. Now I don't need to enter into the backend folder React YT. Now I'll run the command npm run dev. As you can see, running the command, this link URL has been generated. So copy this URL link, and now I'll go to my browser. In this case, I am using my Brave browser. You can use any of your browser. I'll paste the link and I'll click on enter. As you can see, the front end is appearing in front of our screen. Okay. Now let's say for testing purpose, I'm showing you. Let's say I want two customers, two stations, and now I click on generate nodes. As you can see, two customers and two charging stations has been generated, and you can see in the screen. Now let's say I want to add the vehicles number. I can add number of vehicles. For that, brother, click on the depot. I can make that vehicles, increase the number of vehicles. Let's say 04 I am giving, and you can see that 4 has been reflected on the screen. Now let's say I want to give add edge. I have two options. I can edge. Uh, I can add edge manually, or I can add edge randomly. Let's say I want to add edge manually. For that purpose, add I click on add edge. Now I'll go to click on depot. From depot, I let's say I want to add one edge from depot to station 2. Station 2, I'll click on station 2, and the distance will be 20. I'll click on add. You can see one edge has been generated. Similarly, if I click on generate edges, I can see that all the edges has been generated. Now, if I let's say I want to, I can also update the customer pickup and delivery. Clicking on the customer pickup and delivery, I can see you can see one dialog box has been opened. Now I can give value according to myself. Let's say I'm giving it 22, and now it is 45. Click on save. You can see it has been reflected in customer one. Similar way, we can do that. Now, after this is for the for user side, user will provide this value, and the changes will be reflected on the screen. We can move the nodes as well. Now, after that, to find the solution, I'll click on that find path. Clicking on the find path, you can see solution is provided using CSP, that using heuristic and using meta heuristic as well. So now this functionality I'm not explaining. This will be explained by my fellow members. Clicking on this one of this option, you will get the answer according to the algorithm. Okay, that's all from my side. Thank you.
Hello, my name is Shogata Dole. My roll number is 2411 AI20. I am working on Z3 solver to solve this complex AVRP problem. So first let us look the mathematical modeling intuition for this problem. So behind this EVRP model, our aim is to find the optimal routes for electric vehicles to serve customer demand and recharge whenever needed and return to the depot while minimizing the total operational cost. The key challenges is managing multiple constants like vehicle have limited battery capacity, load limits, and must stop at the charging station if energy drops too low. Moreover, we allow partial pickup and deliveries, making the model more flexible and realistic. So our ultimate goal is to construct a feasible and cost-efficient round cost trip that obey all the energy and load and route conditions. So the next thing we have created some decision variables. We have defined this x of v of I of j. This is a Boolean variable that indicates whether the vehicle v it will travel from node I to j or not. Then another variable that is v of energy of vi. This will tracks the remaining battery level at the each node and load. This will reflect how much weight the vehicle is carrying. We also have pickup amount and delivery amount variable that allow a particular service at each customer node. Charging time that represent how long the vehicle charges at a station. And finally, we use route order to help prevent subtours and ensure the correct visiting sequence. These variables collectively enables the solver to uh, reason about the vehicle behavior at every step. Next thing is objective function. We look at the objective function now. We have used a multi-objective approach where the solver minimizes three things. First thing is total distance traveled based on the path decisions. Second thing is total energy consumed calculated as a different from maximum battery level. And the third thing is total charging time, which helps reduce idle time at stations. This comprehensive cost function ensures that the routes we generate are both efficient and realistic under EV construction. Now we will look at the constant. Our model enforces a set of critical constraints to ensure valid routes. Route-wise, we enforce flow conversation, meaning a vehicle must enter and exit each customer node. Every vehicle must start and return to the depot, and subtours can be avoided using visiting order. For energy, we simulated battery draining based on the distance and the current load and enforce minimum battery thresholds. Vehicles can only charge at designated station, and their charging time depends on the energy gap. Lastly, we pick up the deliveries. We allow partial quantities while ensuring the load never exceeded the vehicle capacity. To solve this complex problem, we have used Z3, that is a powerful SMT solver. All constants and decision variables are encoded symbolically, and we use Z3 optimize function that interface to minimize our objective function. When the solution is found, the solver provides a complete route plan for each vehicle along with their battery and load states at each step. It also tells us when and where the vehicle should charge. This CSP-based approach provides a robust and scalable solution to this EVRP. So now I will give you a small demo regarding this application. So suppose there are total 4 customer and 2 station. So we will first generate all these nodes and we'll randomly generate edges. So these two are the charging station. This one is depot and other 4 are customers. Then we will click on this CSP using Z3 and it will send the data at the backend. So the Z3 solver takes a little bit time. Once once it is solved, the output will be shown here in this command prompt as well as the output will be reflected at the front end as well. Here we can see that it has given the route like it will travel from depot to customer 2 and it will deliver 27 kg and pick up 25. Like this it has done for vehicle 2 and as well. Here we can see these dotted animated are the path that the vehicle will cover. Thank you.
Hello everyone. Today I'm presenting meta-heuristic approach to electric vehicle routing problem using genetic algorithm for energy optimized logistic. Why I choose meta-heuristic? Because classical optimization struggle with combinatorial explosion. What it means in problem like EVRP, the number of possible route combinations increase exponentially with the number of vehicle, customers, and constraints. Classical algorithm like linear programming, branch and bound become infeasible for large instances due to the massive search space, making it computationally expensive to find optimal solutions. Second is dynamic constraint. Real world factors such as battery depletion, charging station availability, and varying vehicle load introduce time dependent and non linear constant. Classical methods are not naturally suited to handle this changing condition during the solution process. Meta heuristic like genetic algorithm can flexibly adapt to this constant during optimization. Genetic algorithm overview. Algorithm inspired by natural selection. First one is population. What is population? A set of possible multi-vehicle EV routes. Second, selection. Choose route set with lowest total energy usage. Third, crossover. Combine part of two vehicle route plans. Fourth, mutation. Randomly adjust route to explore new possibilities. Last, fitness. Total distance energy used across all the vehicle. Now, my algorithm execution. The algorithm follow this cycle. First, it initializes population with random feasible routing plans. Second, it evaluates all individuals using the fitness function. Third, it applies selection, crossover, mutation to generate a new population. Last, repeat for a fixed number of generation until convergence. The best individual from the generation represent the most efficient routing plan found by the algorithm. What is problem complexity? There is NP-hard problem like VRP, ERP become exponentially complex as node and constant growth. Multi-constant optimization. It includes route optimization, battery uses, recharging needs, and capacity. Last, real-world relevance. EV adoption demands new logistic model that classical algorithm can easily solve. Genetic pressure in genetic algorithm. Better individuals are more likely to be selected for reproduction. Last, balancing exploitation of good solution and exploration of new possibility. And technique, tournament, roulette, wheel, and rank selection. Advantages of genetic algorithm approach. It handles multiple vehicles, pickups, deliveries, and charging constants. Second, it easily extendable to incorporate more realistic features. Example, time, windows, charging queues. It provides good approximate solution in reasonable time. And what we focus on future work, the first state, it add time window constant per customer. Second, model real-time traffic or delays. And explore other algorithm like anti-cloning optimization, simulated enabling, real-time adapting routing. The references are deep documentation for genetic algorithm and research papers, many research papers that I read for this EVRP problem, and some course materials which is very beneficial to find this to solve this problem really. And thank you so much.
Myself Aditi Thakur, and today I'm going to discuss A-star search in electric vehicle routing. So, how A-star search is going to work? So, here I'm using heuristic, which is Euclidean distance, and it is stored in a matrix. The estimated cost of node is Gn plus Hn, and hi, myself Aditi Thakur, and today I'm going to discuss A-star search in electrical vehicle routing. So, how A-star search works? So, here I'm going to use heuristic, which is Euclidean distance, and it is already stored in a matrix. Also, the total Myself Aditi Thakur, and I'm going to discuss about A-star search in electric vehicle routing. Let's get started. So, A-star search in electric vehicle routing. Here I'm using Euclidean distance as the heuristic, and the total cost of the node is Gn plus Hn, where Hn is the heuristic value. It means uh, the actual cost to reach a node is Gn, and Hn is the estimated cost to reach goal. A star is used because it gives me a optimal solution. It is guaranteed to provide me optimal solution, and it doesn't unnecessarily waste time like brute force or Dijkstra's algorithm. Implementation details. Here I am using distance matrix in which each of the element is going to show me the distance between I and j. So it is a distance matrix, and the data structure which is being used is the priority queue, in which I am storing the nodes which are yet to be explored. Also, there is came from which keeps the track of the path. I also have G-score, which shows me the best cost till now found. Here only some nodes are explored which have lower cost. Not all nodes are explored. Outing and energy management strategy. So, outing and management strategy, how I'm going to save my energy or the fuel. Here, the vehicle is going to go to the charging station if the battery falls below 15%. Also, I'm going to repeatedly apply a star between customer to customer nodes, customer to depot nodes, and as well as customer to charging station. The customer stop is split between vehicles. Output is in the form of JSON file, and it shows me the path for each and every vehicle. My main goal is to optimize the energy used. Okay, so this is the future work and extension. I can also apply a star to some bigger areas or like a city. Also, I can apply the real-time constraints like traffic and also a time window. For example, if a customer wants the delivery between from 2 to 4 p.m., also I can also check for the charging station queues. It means that a charging station can only charge a limited amount of vehicles at the time. So the waiting time of the vehicle, as well as I can also merge machine learning.